when we take this bunch of particles and these particles dissolve in and among water, strong means out of those 12 particles, virtually all of them will dissolve or dissociate. O's to H's with masking tape, and the bariums are all by themselves, and the O is taped to the masking tape. Water doesn't break up our masking tape. So when these particles are breaking up in water, we're going to say that water doesn't break that bond. What I would like you to do now is show what happens when that stuff dissolves completely in water. You'll be able to tell me how many OH free OH minuses there are, and you should be able to tell me how many free barium plus 2s there are. Spend 30 seconds and see if you can answer that.
24 OHs and 12 barium.
Okay, Katie, that. So what I would like you to do now is show me barium hydroxide where only 20% of the stuff is dissociated, and by extension 80%, listen, 80% of the particles remain associated as a solid. Do that now, please.
Because that's the 20% that's associated.
Tabletop. The person who stays is going to explain to the other people who are there what the thinking was that led to the chips being arranged that they are, the way that they are. Anyway.
So we can't round up. Two random particles that have fully dissociated in the water, while the rest of the solid stayed as plus one. So this is 80% of the whole. Like when you
acid and base. Oh my god, my arm is heavy.
If it's a good model, then you should be able to come up with some fairly good what-if questions. Listen for one, sister, go.
Suppose we put hot water instead of cold, would the dissociated percentage go up?
That's a very good question. What's your gut feeling? What do you think will happen process-wise? Just
I think it would, and it doesn't.
How come?
I think it would, because hot water generally makes products or salt or whatever you put in it.
We said that barium hydroxide is 80%, and that 20%.
time out, back up. We talk about barium hydroxide particles. Go ahead.
Yeah, barium hydroxide particles. So how many hydrochloric acid will it take to dissociate?
Back up. How many hydrochloric acid particles? Go ahead.
Hydrochloric particles will it take to dissociate this whole paradigm?
That's a good question. Especially because that.
What if one of the hydrogens from one of the other hydroxide particles were to form with a different hydroxide particle to form H2O? Or could that happen?
Wow. Okay, let me see if I've got this straight. So I've got an OH particle here, and I've got an OH particle here. Are you asking what would happen if this H stuck onto this OH? Well, can I partly answer that? What would this be left as?
An oxygen particle.
And what would the charge on it be?
Negative.
-2. Anish.
If you were to add a single barium particle, would it pair up with a hydroxide particle and become part of like the solid and leave the rest dissociated because it's only 20% dissociated?
That's a brilliant question. And when you what did we get?
Oh, I know. So reds are hydrochloric, blacks are barium, and where's the
Stick to to one of the 5 free OHs, forming water. That will happen, watch my hands. That will happen again, 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 and again. Let's make sure that we've got those 5 new waters formed. Let's take our waters and let's pick up the waters, the 5 waters, and just put them to the side of the beaker. Just because they're getting a little bit crowded in there. For every 5 of these, you need 1 that isn't joined. See, 1 out of 5, 20%. For every 5 that are still binded to each other or bound to each other, there's 1 that will be free. So, do you have any free hydroxides right now? No. So let's go back to this. If you don't have any free hydroxides, then some more hydroxides need to be freed up on a roughly 1 to 5 scale. So let's go free up an appropriate number of hydroxides.